Astronomy, the Science of the Heavenly Bodies, by David Todd. Chapter 10. Kepler, the Great Calculator. Most fortunate it was for the later development of astronomical theory that Tycho Brahe not only was a practical or observational astronomer of the highest order, but that he confined himself studiously for years to observations of the places of the planets. Of Mars, he accumulated an especially long and accurate series, and among those who assisted him in his work was a young and brilliant pupil named Johann Kepler. Strongly impressed with the truth of the Copernican system, Kepler was free to reject the erroneous compromise system devised by Tycho Brahe, and soon after Tycho's death, Kepler addressed himself seriously to the great problem that no one had ever attempted to solve, namely, to find out what the laws of motion of the planets round the Sun really are. Of course, he took the fullest advantage of all that Ptolemy and Copernicus had done before him, and he had, in addition, the splendid observations of Tycho Brahe as a basis to work upon. Copernicus, while he had effected the tremendous advance of substituting the Sun for the Earth as the center of motion, nevertheless clung to the erroneous notion of Ptolemy that all the bodies of the sky must perforce move at uniform speeds and in circular curves, the circle being the only perfect curve. Kepler was not long in finding out that this could not be so, and he found it out because Tycho Brahe's observations were much more accurate than any that Copernicus had employed. Naturally, he attempted the nearest planet first, and that was Mars, the planet that Tycho had assigned to him for research. How fortunate that the orbit of Mars was the one, of all the planets, to show practically the greatest divergence from the ancient conditions of uniform motion in a perfectly circular orbit. Had the orbit of Mars chanced to be as nearly circular as is that of Venus, Kepler might well have been driven to abandon his search for the true curve of planetary motion. However, the facts of the cosmos were on his side, but the calculations essential in testing his various hypotheses were of the most tedious nature, because logarithms were not yet known in his day. His first discovery was that the orbit of Mars is certainly not a circle, but oval or elliptic in figure, and the Sun, he soon found, could not be in the center of the ellipse. So he made a series of trial calculations with the Sun located in one of the foci of the ellipse instead. Then he found he could make his calculated places of Mars agree quite perfectly with Tycho Brahe's observed positions, if only he gave up the other ancient requisite of perfectly uniform motion. On doing this, it soon appeared that Mars, when in perihelion, or nearest the Sun, always moved swiftest, while at its greatest distance from the Sun, or aphelion, its orbital velocity was slowest. Kepler did not busy himself to inquire why these revolutionary discoveries of his were as they were. He simply went on making enough trials on Mars, and then on the other planets in turn, to satisfy himself that all the planetary orbits are elliptical, not circular in form, and are so located in space that the center of the Sun is at one of the two foci of each orbit. This is known as Kepler's first law of planetary motion. The second one did not come quite so easy. It concerned the variable speed with which the planet moves at every point of the orbit. We must remember how handicapped he was in solving this problem. Only the geometry of Euclid to work with, and none of the refinements of the higher mathematics of a later day. But he finally found a very simple relation which represented the velocity of the planet everywhere in its orbit. It was this: if we calculate the area swept or passed over by the planet's radius vector, that is, the line joining its center to the Sun's center, during a week's time near perihelion, and then calculate the similar area for a week near aphelion, or indeed for a week when Mars is in any intermediate part of its orbit, we shall find that these areas are all equal to each other. So, Kepler formulated his second great law of planetary motion very simply. The radius vector of any planet describes or sweeps over equal areas in equal times, and he found this was true for all the planets. But the real genius of the great mathematician was shown in the discovery of his third law, which is more complex and even more significant than the other two. A law connecting the distances of the planets from the Sun with their periods of revolution about the Sun. This cost Kepler many additional years of close calculation, and the resulting law, his third law of planetary motion, is this: the cubes of the mean or average distances of the planets from the Sun are proportional to the squares of their times of revolution around him. So, Kepler had not only disposed of the sacred theories of motion of the planets held by the ancients as inviolable, but he had demonstrated the truth of a great law which bound all the bodies of the solar system together. So accurately and completely did these three laws account for all the motions that the science of astronomy seemed as if finished, and no matter how far in the future a time might be assigned, Kepler's laws provided the means of calculating the planet's position for that epoch as accurately as it would be possible to observe it. Kepler paused here, and he died in 1630.